let me give you more exercise, and this is going to be slightly more difficult. Okay, this is an exercise for you. So ready with pen and paper? Okay, this is the problem of what we call approximate degree. Okay, what is approximate degree? Suppose you are given a Boolean function that means it takes an n-bit string and outputs a bit. Okay, and now you want to write it as a polynomial. What does it mean? You want to write it as a polynomial in x1 to xn such that the value here matches at all the 2 to the power n possible inputs. It's clear that there are 2 to the power n possible inputs, that many strings, my polynomial, and you can do it, but that's kind of expensive in the sense that you need a very high degree polynomial. So what people are interested in is it possible to approximate this function with a polynomial which has small degree? The question is clear. What does it mean? You want degree polynomial p such that for all x, let us say the difference between px and fx is less than some constant, and for REs we will just say 1 by 3. Okay, so this is first the notion of approximate degree. So let us take some time to absorb it. Once more, we are given a function, we want to understand what is the best, in some sense, polynomial representation. Okay, actually lot of it is known. It is known that if you want to have a polynomial representation of it, of this certain kind, then there is a unique polynomial. So remember, now your x1 to xn are real. So this is a polynomial where your coefficients are coming from real. In spite of that, there is a single polynomial which agrees with this function on all endpoints. This is one way in which you can say that your polynomial represents a function, but this is very expensive in the sense that you need a high degree. So what people mathematically are interested in is it possible that there is a small degree polynomial which is close to f? What does it mean close to f? For every input, it should not be it should not be away from fx by more than 1 by 3 distance. Clear? And now we are interested in finding a smallest degree polynomial. Now, one thing to notice is, since your input is only 0, 1, I never need a degree higher than 1. My x1 square is equal to x1. I just want to make sure that my polynomial agrees at these points, right? So I am only interested in the value at these points. So there is no point having x1 square in my polynomial. I can just replace it by x1 and get the same thing on all of these to the power n points, right? So that means my polynomial if you think about it, it will look like some coefficient of s multiplied by the monomial where s. Right? So there are at most 2 to the power n terms in my polynomial. Right? Is this point clear to you? This is just to emphasize what we are doing, right? And just to tell you, this has problems in giving circuit lower bounds, secret sharing schemes, learning theory, quantum computing, there are surveys about this approximate degree, and it has applications in many areas in theoretical computer science. Okay, so now this is a problem, and one of the reason why this is interesting is because there exists a linear program for it. Now, can you make a linear program for it? What would you want to minimize? Right, this is going to be an issue. Now you realize that degree is integer, right? So minimizing degree, you should kind of realize that, oh, that doesn't look like a linear thing. That is going to be a problem. Okay, so we are going to slightly change our problem, and we are going to say, given all degree D polynomials of this kind, because you don't need higher degree, what is the best approximation can I get? And then I will say, oh, for 100, do I get 1 by 3? For 200, do I get 1 by 3? And as soon as I get 1 by 3, I will say, okay, I am done. Right? So in terms of polynomials, this is not very expensive because I just have to repeat my procedure n times. Right? So this is okay. This is number of variables. There is still one extra n, so it's not very expensive. But now this, can you write it as a linear program? My claim is you can. So write a linear program. What are the variables? What are the constraints for this problem? And this is interesting. This is not that straightforward, and I would be happy to explain any doubt here in terms of the definition of. Remember, this is a polynomial in R to the n. That means the coefficients are coming from real numbers, right? But we only need that it works fine on these Boolean inputs. So I want to create a linear program whose answer will give me what is the best possible approximation. Like, so best possible approximation is like the maximum value of this for any degree D polynomial. So I'm not worried about how big my linear program is, but is there a linear program which captures that problem, right? So you can think of it as, what is the error for a polynomial p? The error is this, and I want to find out the best degree D polynomial which, okay, so this goes in kind of two steps. Generally, when you define the approximate degree, you first fix a constant. You say that I want to be this close to my function. 1 by 3 is an arbitrary choice. It could be 1 by 2, it could be 1 by 100, depending upon your application. Okay, and it turns out that that doesn't affect the degree by much, but that's a separate proof. Now you have fixed 1 by 3, you want to find the smallest degree. That's kind of hard because you are optimizing degree, which kind of goes in the integer way. I can't put it in my constraints. I can't put it in my optimization problem. So I flip the problem. Instead of saying that I want this to hold true, I say let me look at all degree D polynomials and find out what best approximation I can get. And then I will vary D and I will stop as soon as I get less than 1 by 3.
Basically, because of the duality of the situation, you can do this.
Yeah, so here your duality is English duality, okay, not the mathematical linear program duality. Yes. Yeah, you should be very careful now, especially speaking to me, when you use the word dual, right? Because So what should be the variables?
Coefficient
The CI. What were the CS you mean? Okay.
and the approximation bound.
Have you seen the program before? No? Okay. Approximation bound. How do you want to how do you want to represent it? Alpha. Okay. Okay. So now, if these are the variables, what is your linear program? I know you are close to it, but let's see if someone else can answer. You want to minimize something. Minimize bound means alpha, right? Yes. So you want to minimize alpha. Constraint is that what you are saying?
This would, I guess, lead to constraints.
Sorry?
This
Yes. Yes. We will go to that, but this is true for all x, all n bit strings. Is that all? No, 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 no. We are not worried about 1 by 3. You just want to find the best possible approximation here. Is that all? No, you are missing something here.
Alpha greater than
No.
CI.
That you can put if you want, but you know, linear program will take care of it. What else?
You have to check for CI. So like all the CI have to be real, so they can also be negative.
Okay. Yes, but I haven't put the constraint that Ci is greater than or equal to 0.
0 or
No, 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 it won't. If it just was outputting 0 or 1, then the degree would be very high. The point is now it can even answer 0.9 and it is okay. If fx is 1, then I am fine with the polynomial outputting 0.9. But, okay, so how many variables are there?
T plus 1.
What is t?
T.
D? No.
Summation up till and choose D.
Right. So the point is, the one thing which is not clear here is that this is only a degree D polynomial. Right? So then remember, even though it looks like this, x here is not a variable. Right? I have written it like this, but x is not a variable. The variables are the coefficients and they will only go up to the D size subsets. So that would be like n choose 0 plus n choose t, right? So I have these many variables plus 1 for alpha. Is this a linear program? Not yet, because of absolute values. But I am sure all of you can convert it into two constraints, both of which are linear. Okay, and I don't know about many other fields, but at least for quantum computing, this realization was very, very important. Kind of looking at this, changing the problem to the dual nature, and then writing out this thing. This is the only way in which we can bound approximate degree for non-symmetric functions. This is the only technique we know, and people have been working on it for at least 20 years.
Still not practical, right?
Sorry?
The solution is still like exponentially.
Yeah, so at this point you are thinking of solution because you are thinking I will feed this linear program into a linear programming solver. But that is not what is expected here. What happens here is that you are given a function like and or parity, and you want to find out whether its approximate degree is root n or n to the power 2 by 3. So it's never that you're going to feed this into a linear programming solver. That will never give you the asymptotic bound. It will only give it to you for one particular n, and that doesn't give anything. So just this linear program, you can write the dual of it, equivalence, and then you can make many things with it. So even though, and this is another very nice example where you never actually solve the linear program, but the mathematical structure, the beauty of it, which I have talked about, allows you to use this linear program to give lot of information about these things, and we will see it. Okay, so generally our idea is, oh, create a linear program, put it to the solver. That's not it. Okay, like a general stupid course in linear program will just tell you simplex method, take the linear program, put it into simplex method, but there is much more to it, and that's why we have to take the comprehensive view of what linear program is, and we will talk about it. Okay, did I answer your question? So yeah, I'm not worried that I can't solve it by putting it in the linear programming solver. I'm just interested that it is a linear program.